let's get started. For recording purposes, we're doing heat, okay? And on the first slide, you will see this. This here are the basic properties of solids, liquids, and gases. How much of you all have seen this at some point in school? It's usually the first thing your teacher will show you. All right. So I want everyone just to begin to write down the table, draw back the table. I'm going to give you 5 minutes, and then I'll discuss one or two things about it. But I know most of the things I'm going to say. You probably already know it, but I'm still going to say it again anyway. So take 5 minutes, draw it up completely, write it back, and let me know when you are finished. Now, I just want to explain a little bit in detail the forces between the particles. So, solids, right? In a solid, the atoms, like if we had a real powerful microscope, an electron microscope, and we zoom in to a solid. In a solid, the atoms, you will see it's very close together. The individual atoms are close. And the reason for that, you see atoms, not all the time, but a lot of times the atoms are attracted to each other. And the attraction is so strong in a solid, right? I'm going to write solid here so you don't get too, you don't get lost. In a solid, because the force of attraction is so strong, all the particles become close, right, or next to each other. But as we go from a solid to a liquid or a liquid to a gas, the force of attraction gets smaller and smaller and smaller, right? So in a liquid, because the force of attraction is smaller, the particles are a little bit more spaced out because the particles don't really care too much about each other. They're not attracted to each other. So they're not as much attracted to each other, sorry. So they are more spaced out. And in gases, it's the worst. The force of attraction between the particles are so little bit. It's almost like the particles don't even notice each other. They're very far from each other. Now, I just want to point out, different textbooks will say slightly different things. For gases, they might say that the force of attraction is weak. Some textbooks will say very weak, and some textbooks will say no attraction at all. It's basically the same thing, right? Well, what they're really trying to say is the particles don't really care about each other. And even if the force of attraction is so weak in a gas, it's almost non-existent or not even too important. So that's why different textbooks say slightly different things. All right. And to me, for today's class to explain heat, this is going to be the most important thing to understand heat today. Right? So everyone okay so far? That in solids, the atoms are close together, liquids are a little bit more spaced out, and in gases really spaced out. And it all has to do with the force of attraction getting smaller and smaller and smaller. All right? Right. So for those who came in a little late, today's topic is heat. Now, if I were to ask you, what is heat? Like if I were to ask you, why does something get hot? Why when we put something over a fire, like if we have a piece of iron and we put it over a fire, why does it get hot? I just want to make sure that we understand one thing, right? Is everyone aware that when you heat something up, it gets slightly larger? Or how much of you all know of that phenomenon? Like, let me draw a little flame. Let me say we have a ball here, a piece of iron, right? Right? And we were to, yeah, for those who didn't know, right? if we have a piece of iron, right? Like we get a solid sphere of iron, a ball of iron, and it's this size. And then we take the iron and we heat it up. So we put it over a flame. That's supposed to be my representation of a fire there. Did you all know that the piece of iron would actually expand and get slightly bigger? When things get hot, they usually get slightly larger, right? I, you all, I could prove this to you all with something you just see almost every day. In a thermometer, we all know a thermometer, the old time ones, right? The old time ones with the how you call it? With the mercury in it. So I'm just going to draw a little thermometer here, right? So let me say this is a thermometer. And inside, right? And inside the thermometer, it has what? Mercury, right? So let's say this is the mercury as well, right? We all know when it gets hotter, and it's a simple question I'm going to ask. When it gets hotter, will the mercury go up or will the mercury go down? And by the way, the expansion of things applies to everything in science, right? When you heat up something, it's supposed to get larger, everything. Right, we all know when you heat it up, it will go up. The mercury will go up. Now, most people will say, hey, when we heat it, the mercury goes up. You know why it goes up? Because it's expanding. The mercury is expanding. Well, how about we change the language to this? When we heat a thermometer, instead of saying the mercury goes up, we could say the mercury expands. That is why the mercury goes to a bigger height, because it is expanding. So that's a case where you can actually see something expanding because of the change in temperature. Now, right now, I would say we have a decent understanding of heat. But if we went back to the 18th century, right? Let's use your imaginations, right? Let's say you went back to the 18th century with George Washington and whatnot and those guys, and you're wearing those the 18th century clothes and whatnot, and you have a little 18th century accent, a British accent or something like that, right? And you ask somebody what is heat, or why when you put something by a fire it gets hotter, they would tell you something very, very strange, and you might laugh at them. You see, back in the 18th century, they had a theory called what? The caloric theory. And they believed heat was a magical fluid. Imagine that, right? They thought heat was a fluid. And you might think that they are what? Crazy. But let's hear the reasoning behind it, right? We now saw, and they saw it too, when you heat something up, it gets larger. So how did they explain that in the 18th century? Well, according to this, there was a magical fluid called caloric. And when you heat something, it would fill up the object. Just like how you could fill up a balloon with water and it would get larger. The same thing. They thought heat was a liquid. And they thought when you heat up something, you're adding that magical liquid inside called caloric, and it would get what? Larger. I know today we would laugh at them, right? They say, well, these people are crazy. What are they talking about, right? But I'll give you some advice. 100 years from now, what we currently know, people might laugh at us, okay? Also, are you all aware that heat travels from hot to cold? Like, for example, let's say you have a piece of iron and you heat one side and your hand is over here, right? If you heat this side, so this side is hot and this side is cold. When you heat one side of a metal spoon, does the other side immediately get hot? Well, what do you think? If you put a spoon on a stove, does your hand automatically burn instantly as soon as you put it over the flame? No, no, it doesn't. If you take a spoon and put one end over the flame, your hand doesn't immediately burn. It might take a few seconds or a minute for the heat to travel from on one side to the other side. It takes a while to travel. And of course, people in the 18th century or way before the 18th century realized that heat takes time to travel. And they always realize it travel in the direction from hot to cold. So the heat would always travel from hot to cold. How did they explain this, right? Remember, caloric to them was a fluid, so it's made up of particles, right? They said that the particles would repel each other. So when you have caloric, it's like two north poles of a magnet. North and north will repel. The same thing with caloric. They thought all the particles of caloric repelled each other. So they would push each other away, and the direction they would push each other away was from hot towards the cold region. Now, we all know but in this day and age, this is nonsense, right? But in the CXC exam, they could bring questions on caloric. It's like a history question. They like to bring questions on what did the people think about heat in the 18th century? Everyone okay so far? Right? Take down everything on the screen, right? Memorize it for the exam. All right, let me know when you are. All right, so we have a small little game to play here, right? So I think class gets a little boring. So let's see if you all can win the game. So we have a little jester here, and he comes up and he wants you to play a game. So you have to choose two items on the chart, and what's going to happen is squares are going to change color. And if you get your two items are the same color, well, you win. You're going to win a certain amount of points. So choose two items, guys, just for fun, just to relieve the stress and whatnot, or relieve the tension. Choose two items, and let's hope your two items are the same color. Let's see who is lucky and who is not lucky. All right, anybody who won, they get how much points this round? 2 points. Let me know if you won. Oh, by the way, the colors, these colors are kind of similar. Don't mix up the orange. Everything has an orange color, right? This is yellow, 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 and yellow. I don't know why I use yellow and orange. I could have used a better. All right, so you can always let me know if you won or you didn't win, right? Right. Write down how much points you got. So let's see how much you can accumulate at the end of class. All right. All right, let's go. All right. So over time now, right? People began to notice flaws in the caloric theory as the centuries went by. They said, wait now, the caloric theory doesn't really make too much sense. So let's see what they thought did not make any sense. Well, first of all, right, whenever something, all right, they tried to detect, first of all, they tried many experiments to detect this magical fluid called caloric. I mean, if caloric is a fluid, there should be a way to detect it or isolate it or see it or something. And after numerous attempts, they just couldn't find the caloric. So that was one thing wrong, okay? So 2, if different materials are given the same amount of heat or caloric, their temperature increased by different amounts, which indicated that they are receiving different quantities of caloric. Let me break that down simply for you, right? If you have a piece of iron, right? And you have a piece of wood, right? Now, provided the wood doesn't, some pieces of wood, it doesn't actually catch fire. You could put it in fire and it might smoke up and whatnot, but it mightn't, the whole thing won't burst into flames, right? So some wood is like that. Tell me something. If I put a flame underneath a piece of iron and a same exact size of flame underneath the wood. So the iron and the wood have the same exact size of flame. And I let both of them heat up for 1 minute. Now we're going to assume that the piece of wood doesn't burst into flames. Like I said, not all pieces of wood burst into flames. And I let both of them hot with the same exact type of flame for 1 minute. Which one would you rather place your hand on? Would you, after 1 minute, I tell you, rest your hand on one of them. After 1 minute, which one would you rather touch? It would be the piece of wood, because we know from experience iron or metals heat up faster than wood, right? So if two of them receiving the same amount of heat, remember back then they didn't really call it really heat, they blamed heat on caloric. If the two of them have the same exact flame, size of flame, then both of them should be receiving the same amount of caloric. So why is it that both of them have a different temperature after 1 minute? Because after 1 minute, this one might be 100 degrees Celsius, and the wood might only be what? 50 degrees Celsius. So that seems strange to them. Because, let's say, I know I said it back, I know someone probably didn't catch it. If both flames are the same, and both of them are getting the same exact amount of caloric, like they're absorbing this fluid called caloric, well, then both of them should have the same temperature. So that caused some eyebrows to raise. Like, oh, something is making sense here, boy, right? So that is why they just started to debunk the caloric. Also, and if you add a fluid to something and it's supposed to get heavier, I guarantee you, when you heat up something, even though it gets larger, remember we said in the last slide, when you heat up things, it gets larger in volume. But whether it cold or it hot, it's going to weigh the same amount. So if you adding caloric to something, which is a fluid, shouldn't the hotter object be heavier than the colder object? But then scientists realize, wait now, cold objects and hot objects weigh the same amount. So they couldn't have any caloric in it. So for the exam, they could ask you for the 3 reasons to debunk the caloric theory. Take down everything. Let me know when you are finished. All right. So let's see. After the caloric theory begun to how you say get stranger and stranger, and it started not to make too much sense. There was this guy called Rumford, right? He decided to do an experiment. It's called the cannon boring experiment. This is how you say this confuses a lot of people. You all know, because you might not know what I hope you all know what a cannon is, right? You all know long time on those ships, like pirate ships and thing. You have the cannon and have a little it's called this thing here. Oh god, the wick, right? And you will put a cannonball inside. So you all know that inside the cannon, right? Right? There's a hole, right? Where you place the cannonball and then you shoot out the cannonball. I think you all could you all could imagine that, right? Have you all ever wondered where the hole comes from or how they make that hole inside the cannon for the cannonball to fit in? Well, it was a it's not a mold they had. What they will do, right? Let me draw this back, right? Because this was confusing to me too, because this seems like a really inefficient way of making a hole in a solid piece of iron. If you had a solid piece of iron with no holes in it, right? This is already wick here. What they got was a piece of metal, right? And they rested it on that. And what they will do, they will turn this piece of metal like a grinder and slowly grind a hole through the cannon, right? That seems like a lot of work. And to me, that seems like it will take more than one day to grind a hole in a solid piece of iron. Okay? That's like trying to take a screwdriver and you're trying to grind, like you press on it and you try to grind a hole through something that's made of metal, like your refrigerator or a stove or something. Okay? Now, are we all clear that it's two pieces of metal grinding on each other there? Could you all imagine that? Tell me, well, from experience, I don't know if you all play around with tools and whatnot at home and whatnot, right? When you rub or grind two pieces of metal together, right? What do you all notice? Does it get hot? What do you all think? Let me know. Give me some feedback. And have you all ever experienced that? Does it get hot? Yes, it gets hot. If you take a drill, right, those electric drills, and you try to drill a hole, even through a piece of concrete, if it's metal grinding on concrete, you ever touch a drill bit after? It is be super hot. It will blister your hand just by a little touch. Okay? So imagine two pieces of metal sometimes it get red hot. And I don't know if you all can notice it here. This here is the cannon. You can't miss it. This piece here is the cannon. And this here is the piece of metal grinding the hole through the whole cannon. So this piece of metal is connected to this, right? So everything is just going to get very hot. And what they did, this piece here, because remember this piece is connected to this, right? So the whole thing is hot. They would place it in a bathtub of water. And guess what? The heat would start to boil the water. And Rumford, but this is his experiment that he devised, right? And he used the heating of the water to prove something. So let's see what he proved by this. But this took me a real long time to understand in school, because in school, I just didn't understand how the hole was being made, right? I didn't understand that you had a physical piece of iron grinding through that solid piece of metal. To me, it was so inefficient. I couldn't imagine anybody trying to do that in real life now. So I had a real hard time understanding that in school. And it's only after school I realized what was going on, right? So anyway, let's see how this experiment helped to prove a few things, right? When he did his experiment, you don't have to worry too much about the rest of the experiment. He just proved that the from the friction, from the grinding, produced heat. That's probably the most important thing there. That friction produced heat. And then these things began, it became the end of the caloric theory. People started to move away from the caloric theory and started to believe in something called the kinetic theory. Before you start to read everything there, let me just explain the basics. We kind of now know that friction causes heat. When two things hit each other or grind on each other, they produce heat. Scientists now know, well, they're pretty much sure because they could see it underneath a microscope. If you have atoms, right? Let's say this is a piece of metal, and the atoms, you put the atoms underneath the microscope. Once there is a little bit of heat, right? The atoms are always vibrating. The atoms are always vibrating. When atoms vibrate, won't they hit each other? And when they hit each other, they produce what? Friction. And that what? Friction in turn produces the heat. So they realize that atoms are always vibrating. And when they vibrate, they hit each other, and that produces a type of friction, and it produces what? Heat. So they kind of realize, wait now, heat is not really a liquid. Heat is a kind of result of atoms hitting each other, and the friction of it produce heat. And then you realize, wait now, when you heat up something even more, let's take a wild guess. If you were to heat up something more, would the atoms vibrate more, or would the atoms vibrate what? Less? Would the atoms vibrate more, or would the atoms vibrate less? The atoms will vibrate. No, the atoms vibrate more. You know why did they theorize that the atoms vibrated more even before the most powerful microscopes were invented? To produce more heat, and you need more friction. So when something is heated, they realize that the atoms were vibrating way, way, way more, back and forth even more. That means they were now hitting each other with a harder force. And not only with a harder force, they were hitting each other more frequently, hence producing the more friction, thereby representing the higher temperature, right? So we're seeing that heat is not a liquid. It's a result of the amount of vibration of the atoms, okay? So the moral of the story is this: as things get hotter and hotter and hotter and hotter, they vibrate more and more and more and more. And when they get colder, the vibration gets less and less and less and less, okay? Now, I want everyone to take down everything on the screen, give it a read, right? You won't understand everything there. By the way, freezing doesn't mean it reached the coldest temperature. Not because something freeze, it means it has reached its coldest temperature. That's far from the truth. You know how I know that's far from the truth? If water freezes at 0 degrees Celsius. I think everyone knows that. You call it ice. Is it possible to have ice at a colder temperature? Is it possible to have ice at minus 40 degrees Celsius? Yes, right? And by the way, not because something freezes, it means the atoms stop vibrating. I guarantee you, if you put a piece of ice at 0 degrees or even at minus 40 degrees, and you put that underneath a very, very, very powerful microscope, the atoms will still be vibrating. Frozen doesn't mean vibration stops. Frozen just means the vibration, because it's cold, it got a little bit less in the vibrating. It vibrating slower or at a smaller amplitude. The only time vibration is supposed to stop is when we reach the coldest theorized temperature. And I say theorized because we haven't reached the temperature as yet. It's called minus 270 degrees Celsius. This is what we call the coldest possible temperature that might be achieved. It's called absolute zero. We haven't reached there as yet. Scientists are working around the clock to try to achieve that temperature. And they say at that temperature, all atoms will cease to vibrate, right? So maybe when you all grow up, that will be achieved. I doubt it will be achieved in my lifetime, right? So anyway, take down everything on the screen, and I'm going to discuss one or two things that might give a little bit of prominence. Someone asks, well, why they call it the kinetic theory? Well, there's a good reason for it. How much of y'all did this topic called kinetic energy? I did it last term in class. Do y'all remember the formula for kinetic energy? Half mv squared. Y'all remember that formula? Right. Now, you ask yourself, what is kinetic energy? When something is moving, doesn't it have kinetic energy? Look at here. The formula even has a V for velocity. So anything that is moving has kinetic energy. And well, they developed a formula to calculate the amount of kinetic energy. So, and the atoms vibrated, and we now said the heat is being generated because of the vibration of the atoms. Isn't vibration a type of movement? Anything that is moving has kinetic energy. So that's why they call it the kinetic theory of heat, because it's the actual motion / vibration of the atoms that's effectively generating the heat because of the friction, and it's causing the friction. So I hope that clears up the question there. Now, I know some of you all might be confused about number 3, but I have a whole slide dedicated to explain that. Are we ready to move on? Right? Are we ready to move on? Let's go. Right? All right, so we have a little slide here. Someone asked if the electrons of an atom has anything to do with the heat. Not to my knowledge. If it has something to do with heat, the electrons, that's way outside of my my education level. But I don't know if electrons have anything to do with heat itself. All right. So let's talk a little bit. This slide is basically to explain number 3 on the last slide. Okay. So let's see. Heat is a type of energy that may or may not cause a change in temperature. Sounds crazy, right? Because isn't the whole point of heat to change the temperature or to increase the temperature? Let me put it in something that everyone understands. Money. The more money, let's say somebody brainwashes me and somehow convinces me to give you some money, right? If I give you money, let's say every day I walk up to you and I give you $100. So Monday I come and say, hey, look, $100. Tuesday, you get $100. Wednesday, I show up by your house. I'm knocking it off. $100 for you, right? Aren't you supposed to be getting richer and richer every day? Because isn't the point of money? So the whole point is to make you richer. Now, if I am giving you $100 every day, theoretically, you would get richer. So let's go back to the scenario here now. So Monday, I check you, I give you $100, so you get richer, and I'm real sure you get richer, right? It have a richer indicator on top of your house for whatever strange reason. Every time you get richer, it is blink, bing, 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 right? So Tuesday, I give you $100 again. And bing, 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 right? You're getting richer. So, and then Wednesday, I give you $100 again. And the light or the blinker doesn't go off. You did not get richer. But that's strange to me. I just give you $100. How come you didn't get richer? Well, maybe you did something else with the money other than save it. Doesn't that make sense? Maybe you eat the $100. Maybe you have a crazy desire to eat $100 bills. You have a problem, a psychological problem, and you eat $100 bills. I don't know. Maybe you like to burn money. Maybe that makes you happy. So on Wednesday, when I give you the $100, you either eat it or you light it on fire or you rip it up because you like confetti more than money. I don't know, right? But the point is, right? You did something else with the money other than save it. And the same thing happens with heat. Whenever you heat something, not the same thing happens all the time. So let's go have a little diagram here. Right. By the way, it have some sets of atoms here. It have a red set, it have a blue set, right? And it have a yellow set. Which one do you think is the solid? The red, the blue, or the yellow? Let us take a wild guess. Which one do you think is the solid? Right, it has to be the red, right? Because in solids, them I told, well, you all have good memories, right? Better than mine, so sure about that, right? The solids, the atoms are closer together. And you notice as you go this way, the atoms get more and more spaced out. So let me just write the words over it, right? So this is a solid because the atoms are close together. This is also a solid because they're close together. Here you have a liquid because the atoms are more spaced out. And here you still have a liquid. It's a little bit more spaced out, but it's still considered a liquid. It's only when the atoms get too spaced out, you get to call it what? A gas. Are we all in agreement that solid, liquids, and gases are different phases of matter? Can I use that fancy word with you all? Phases. It have a solid phase, a liquid phase, and a gas phase. All right. So let's heat. Let's say this is a piece of iron, right? So we're going to heat this solid piece of iron. Then the iron is going to melt. And then the iron is going to turn into vapor, steamed iron, right? So let's start off with, let's say the iron is at room temperature, 27 degrees Celsius. If we heat it up, we know we could heat iron and it could still remain a solid. It would just be hot iron. Let's say we heat it up to, let's say 200 degrees Celsius. The heat did what? Didn't the heat make it space out more? Look at it. I know the space and kind of close, but the second solid, you all notice that the how you call it? The spacing of the atoms are a little bit more spaced. And we know why. I just explained that when you heat up something, it vibrates more. And when it vibrates more, it causes the atoms to space out a little bit. Now, two things to notice here. When we heat up the iron, was there a change in temperature? It's a very simple question. I'm not trying to trick you. When we heat up the iron, is there a change in temperature, right? So yes, there is a change in temperature. Is there a change in state? Was there a change in state? No, because it starts off as a solid and it ends up as a solid. So there's no change in state. All right. So we know eventually if we heat up iron, it have to melt, right? It have to change into a liquid. So look what's going to happen here. it's going to go from a solid to a liquid. But look at what happens when it melts, when it now melts. I know it seems crazy. This, you might think because you're heating it up more, right? The temperature is supposed to change. But you see, when things now melt, the temperature doesn't change, you know. But even though there's no change in temperature, is there a change in state? Well, the obvious answer to that question is yes, because it's changing from a solid to a liquid. Now, it brings me back to the money. The whole point of money is to make someone richer at first glance. But that is what most people think. What's the point of heat? Isn't the point of heat to make something hotter? And it did start off like that. We applied heat and it went from 27 degrees to 200 degrees Celsius. And then we applied more heat. But when we applied more heat, the temperature did not change. It's like when I gave you more money on Wednesday, you did not get richer. And we theorized that you were doing something else with the money other than the proper thing. You see, when something changes state, the heat energy that you give it doesn't go into what? Changing the temperature. The heat energy is invested into changing the phase of the material. So you still have the energy. It's just the energy is going into doing something different other than changing the temperature. And whenever you have heat energy not changing the temperature, anybody knows the name given to that type of heat? Whenever heat energy does not do what is expected, it instead changes the phase rather than the temperature. Right, you call that latent heat. Latent comes from a Greek word. It means hidden, right? It's hidden heat energy. It doesn't go into change in temperature. It goes into change in the state. So after now the latent heat is applied, it will change into a liquid. So the atom space out enough to call it a liquid. And then you could heat the liquid from 200 degrees Celsius to probably about 500 degrees Celsius. This is normal heat energy. But then eventually it's going to change into a gas at 500 degrees Celsius. It's a liquid at 500 degrees Celsius, but when it now changes into a gas, even though you're giving it heat energy, it does not go into the temperature change once again. Instead, that latent heat goes into changing the state from liquid to gas. So whenever there is a state change from solid to liquid or liquid to gas, your thermometer is not supposed to move up or down. The thermometer is supposed to stay on one value because at that particular point, there is not going to be a change in temperature. All right. Now I need for everyone, I hope that makes some amount of sense, right? I would like you all to take down this here. I'm going to circle exactly what I want you to take down. You can leave out the 3 containers at the top. You think you all can write that down in 5 minutes for me? Right? Let me know when you are finished. Great. Let's go. All right, so we have a little game here, right? You have to try to guess what that picture is. Anybody wants to take a guess of what it could be? I'm only willing to remove 5 squares, but take a guess. Let's see if you can get it out. Oh man, oh, that's too easy. Somebody said trees. Haha, wrong. Somebody said it's a snake. Somebody says it's a fish. Somebody says an iguana, a rat. What? Let me remove one panel for you. All right. Hope that makes it easier there. Somebody says a dragon, an alligator. What? Let's see. Somebody said a deer. What? Why is dragon so important? It's so popular. But most people got it correct. I just like reading the wrong answers here. A snake, a snail, a parrot. Somebody says it's me. All right, let's see what the correct answer is. It's a duck. Most people got it correct. Most people got it correct. A mallard duck. What do you mean how? That's just how it is. I don't have an explanation. All right, let's move on. Let's move on. Right, that's 2 points if you got it correct. All right, let's talk about some heat transfer. I just want to get all the written part of this out today, so next week we could just do all the calculations, right? Heat transfer. Heat transfer is all about how heat can travel from one point to another. Let's start off with to me, the easiest one to explain. Conduction, okay? Let's say we have a piece of metal and one end we light a flame. Now we already established that the heat, right, does not immediately go to your hand side. It takes some time for the heat to travel. It may take a minute, it may take 2, but it takes time. And we all know, I just refreshing your memory, that heat has something to do with the vibration of the atoms. And the more it vibrates, the more heat it has. So let me tell you why it takes time to travel from side A all the way to side B. When you heat this side, this atom begins to vibrate. And as you heat it more, it begins to vibrate more and more and more. Eventually, it will vibrate so much, it will hit the neighboring atom, right? And when it hits the neighboring atom, he will begin to vibrate. And when he begins to vibrate, eventually, he going to what? Hit the one next to him. It's almost like a domino effect. And eventually, it will reach what? Point B. But this vibrating and influencing your neighbor to also vibrate takes what? It takes time, okay? So you call this type of heat transfer conduction. And look at the kind of definition here, or the reason for it. The transfer by particle vibrations and collisions. I hope that makes sense. When one starts to vibrate, it will collide with its neighbor and encourage its neighbor to vibrate as well. This type of heat transfer, once again, is called conduction. There's another type called convection. Quick question, which one is more dense? Like, I'm going to draw 2 scenarios here. I'm going to draw atoms close together. I'll call this scenario A, and I'm going to draw one where the atoms are slightly more spaced out. Which one is more dense, A or B? In other words, I'm asking, when particles are close together, is that more dense or less dense? Right. When density is a measure of how close the particles are. The closer the particles, the more compact it is, the more dense it is. So A is more dense and B is what? Less dense. Which one floats? More dense or less dense? I'm going to repeat that question. Which one floats? More dense or less dense? Which one floats? Right. So things that are more dense will what? Sorry, things that are less dense will float. Things that are more dense will sink. So I want you to take a guess here, right? Let's say A and B is the same exact material. Which one do you think is hotter, A or B? Take a wild guess. Which one do you think is hotter, A or B? Whoa, lots of people getting this wrong. Asking you which one is hotter. B has to be hotter. Remember what we said, as things get hotter, they get more spaced out. The atoms vibrate more, so they push each other apart. So B is hotter. For those who got it wrong, you think you understand it? The hotter something is, the more spaced all the atoms are, right? We said that for how much slides coming down. All right. So the moral of the story is this. Hot things float. I have it on the screen here. Look at it. Hot things, the atoms are more spaced out, hence they are less dense, hence they float. Cold things are more dense and they what? Sink. Okay? That is why if you sit down directly underneath an AC, an air condition, you feel cold because the air coming out of an air condition is cold. It's more dense and it sinks right down and falls on you. Okay? So let's say we have heat can be transferred from one point to a next point because of the difference in densities. Let's look let's look at a pot of water. When you have a pot of water, we know a pot of water, when you light it, it doesn't get hot immediately. It might take a whole half an hour if it's a big pot of water. Let me just have a little pot of water here. So when we heat this pot of water, does everyone agree that this area here that's close to the flame will get hot first? So the atoms would be spaced out plenty. This area, because of this particular area, right? Because this particular area is getting hotter, it is getting what? Less dense. When I say less dense, it's less dense compared to everyone else around it because the rest of the area is what? Cold. What do you think is going to happen to the liquid in this area? It will do what? It will start to do what? Float, or it will start to what? Rise. And when it rises, the reason it rising, it's because it's what? That area is less dense. And when it rises, it carries the heat with it. And of course, when this area rises, the cold water will take its place, but it's a trap. When the cold water takes the place of the water that just rose because of its small density, the cold water falls underneath the heat now, and he begins to heat up, and he will begin to rise. And eventually the whole pot will get hot. Okay? In this case here, the heat transferred throughout the pot, it's not due to the actual vibration of the atoms hitting each other like in conduction. The heat is being transferred due to different densities caused by the different temperatures of the water. Everyone okay with that? And I have the definitions here. Everything I've seen already summarized in the table. And the last one is radiation, right? The last one is radiation. The first two, conduction and convection, the heat needs something to travel through. You call that a medium. In this case here, in the first case, the heat is traveling through the piece of iron. The piece of the iron is called the medium. It allows the heat to transfer through it. The second one, there is a medium because what? The water allows the heat to flow from one point to the other. But radiation does not need a medium. Let me explain why, right? The sun produces heat. Is there anything in between the sun? We have a place. Oh, let me say this is the sun here. Let's say this is the sun here, right? So that's the sun. And over here is Earth. We all know heat goes from the sun to the earth. But is there anything in between the sun and the earth? Is there a big piece of iron for conduction to happen? No. Is there a big pot of water that surrounds the sun and earth for the heat to flow from the sun to the earth? No. So the heat from the sun to the earth actually reaches in the form of a wave. It's a special type of wave called electromagnetic waves. And it requires no medium to flow through, right? So all that heat we receive from the sun is not from conduction, it's not from convection, it's by a different type of heat transfer mechanism called radiation. And that radiation is made up of something called electromagnetic waves. And this is a depiction of how it would look if we could see it, but we can't really see it, right? But when we monitor the electromagnetic waves, it looks something like this. Don't worry, electromagnetic waves is a chapter by itself in physics, right? So just one thing I want to update here, right? Or I have it here, right? Medium required, yes. Everything here, how it occurs, the speed, an example. Radiation is actually the fastest. Radiation actually travels at the speed of light, okay? Convection is moderate and conduction is very slow. Take down everything. I hope it makes some sense and let me know when you are finished.